Quantum computing is moving from theoretical physics to industrial application. To reach the scale of fault-tolerant systems, the industry must navigate the physical, economic, and geopolitical realities of its underlying supply chain. Superconducting qubits require temperatures near 10 millikelvin. At higher temperatures, random thermal energy excites the qubits out of their quantum states, causing rapid decoherence. Reaching these temperatures requires an ultra-rare isotope called helium-3. It is a stable fermion derived almost exclusively from the radioactive decay of nuclear weapons stockpiles. Simultaneously, the manufacturing of the required cryogenic hardware, spanning the processors, control electronics, and specialized cabling, is concentrated within a single geographic corridor in the Netherlands. Scaling a quantum data center is a challenge of navigating a fragile ecosystem where coolants and cabling possess the geopolitical sensitivity of weapons-grade uranium. Superconducting qubits must operate at 10 millikelvin, roughly 150 times colder than the cosmic microwave background of deep space. This extreme environment is the only way to prevent random thermal energy from destroying the qubit's fragile quantum states. The only technology capable of providing continuous, reliable cooling to these levels is the dilution refrigerator. This system relies on the unique quantum statistical properties of two helium isotopes. Helium-4 is a boson that becomes a superfluid at low temperatures. Helium-3 is a composite fermion, bound by the Pauli exclusion principle. When a mixture of the two is cooled below 870 millikelvin, it spontaneously separates into a concentrated helium-3 phase and a dilute helium-4 phase in thermodynamic equilibrium. Cooling occurs at the boundary between these two phases. When helium-3 atoms are forced from the concentrated phase into the dilute phase, they absorb energy from their surroundings. This process is thermodynamically analogous to evaporation, but it occurs entirely between two liquid phases. Precise hydrodynamics are required to keep the system efficient. To suppress convection that would destroy the cooling effect, modern cryostats route the concentrated stream upward and the dilute stream downward. This allows the outgoing cold stream to pre-cool the incoming warm stream. Because this cycle depends on fundamental quantum statistics rather than chemical properties, helium-3 is the only stable fermionic working fluid available to cryogenic engineering. There is no physical substitute. Extracting helium-3 from natural gas is staggeringly inefficient. In concentrations of only 70 to 240 parts per billion, the energy cost alone to isolate the isotope from liquefied bulk helium is estimated at up to $300 per liter. Instead, the world relies on an artificial supply chain. Helium-3 is a byproduct of the nuclear weapons industry. It is derived from the beta decay of tritium, a radioactive isotope used to boost the yield of thermonuclear warheads. With a half-life of 12.3 years, tritium decays into helium-3 at a steady rate of 5.6. High-purity variants can cost upwards of $10,000. The primary working fluid for next-generation computation is trapped in a zero-sum inventory game, fundamentally bounded by the management of international nuclear arsenals. Procuring the dilution refrigerator itself requires significant capital and patience. Due to the precision engineering required, delivery lead times reliably stretch between 6 and 12 months. As qubit counts scale, the system hits the I/O wiring wall. Standard coaxial cables running from room temperature to the millikelvin stage introduce a thermal load that can overwhelm the refrigerator's cooling capacity. This diagram shows the foundational layers required to build and operate a superconducting quantum computer. It reveals that critical enabling technologies, from the foundries to the cabling, are heavily concentrated within the Delft-Leiden corridor in the Netherlands. Delft Circuits provides the only commercial solution currently capable of bypassing the I/O wall at scale. Their flexible superconducting strip lines condense 256 high-frequency channels into a single loader, while delivering a thermal load 10 times lower than standard coax. This cabling links directly to off-the-shelf processors from Quantware and modular control electronics from Q-Blocks. Both firms are deeply integrated into this localized hardware ecosystem. The extreme difficulty of millikelvin cooling has forced a hyper-specialization that concentrates global hardware reliance into this single, subsidized Dutch ecosystem. Governments now treat quantum computing as a dual-use technology. A mature system could theoretically break current cryptographic standards as early as 2030, a milestone known as Q-Day. Following U.S. bilateral pressure, the Netherlands has broadened its national export control regime to explicitly include quantum cryogenic systems. New restrictions enacted in late 2024 require global export licenses and rigorous internal compliance programs. These regulations introduce significant delays for international hardware deployment. Simultaneously, the WIFO Act grants the Dutch Bureau for Investment Screening broad powers to block foreign acquisitions of local quantum firms. For highly sensitive technologies like quantum, the law triggers mandatory reporting for the acquisition of as little as 10% of voting rights. This applies even to early-stage venture capital and startup funding. The quantum supply chain is fracturing into allied blocks. A hardware build anywhere in the world can now be delayed or halted by a single Dutch regulatory decree. Protracted lead times and the structural helium-3 deficit have ended just-in-time procurement. Organizations must now secure multi-year material offtakes at the inception of a facility build. Because a single large-scale helium-3 charge costs over $100,000, facilities are migrating towards a circular economy. Operators must now implement closed-loop gas recovery and purification infrastructure to recycle their initial charge indefinitely. To reduce reliance on specialized cabling, the industry is accelerating the development of cryo-CMOS. This involves moving the control electronics inside the cryostat itself, operating at the 4 Kelvin stage. By solving the I/O wall internally, these architectures reduce the number of cables traversing the thermal gradient. This lowers the absolute cooling power required, effectively reducing the volume of helium-3 needed per processor. In the coming years, national quantum readiness will depend on the strategic capability to secure, recycle, and defend the hyper-fragile supply chain operating silently beneath the chips.